So we just connected kind of discrete and continuous time, and we kind of want to keep two things in mind. One is this discrete time, discrete state space Markov chain, a random walk S, and we've just moved over to this scaled, interpolated random walk W delta, and that is going to be moving in continuous space and continuous time. So the time coordinate is now between 0 and infinity, a real number. It's not negative, and x is going to be all real numbers, and so x is the position of the random walk, right? So here in this video again, here you have things in 3 dimensions. We're thinking of 1 dimension, and the blue dot there is going to have position x at time t. And to connect it back to the discrete time chain, you have these conversion rules. If you look at a continuous time index t, continuous time t, and you have delta t, which describes the amount of time that passes once this Brownian particle gets hit and moves and gets displaced. T divided by delta t is going to be the number of time steps that has passed, and of course each time step corresponds to this Brownian particle getting hit either from the left or the right. And the position of it, if it's some x, that's a real number, and the amount it moves every time it gets hit is delta x, then what's the position in a discrete state space? Well, it's just the integer part of x divided by delta x. And so what I'm going to be thinking of now is kind of this conversion between discrete and continuous time, where I'm looking at the position of the random walk, the discrete time, discrete space random walk at time k, and it's in position n, and n here is some integer, and k is a natural number, and I'm going to set that equal to f of t x, where t is non-negative real, and x is the position in the space. It's a real number, and using to equate one side to the other, I'm using this conversion here to go from every x to an n. You follow this procedure, integer part of x over delta x, and k is obtained by taking the integer part of t over delta t. And so now this is going to be sort of a crucial equation for us, and I don't want to jump ahead and try to explain what it means yet, but this equation is going to lead us towards the transition probability of the Brownian motion, and we'll see how to do that in the next clip. For now, let me just try to prove this. So this, what we now have is this function f of tx. We have a function defined on this domain, and the claim is it's going to be satisfying this property, where it's the function at f of t and x is the average between these two values of the function at sort of neighborhood points. So if we think of t, time t and x as kind of the center point, then it's an average of the function f evaluated at the previous time step t minus delta t, and the next position x plus delta x, and also the position below x minus delta x evaluated at again the previous time. So time t there is sort of one index forward, time t here is one index back. So this is talking about, it's relating present time t to past t, or past time t minus delta t, and the position in space either moves up or moves down, or you could think of it about as the left and right, because we're dealing with one dimension. And so let me just quickly kind of go over the proof of this, and then we'll see sort of how this leads to the transition probability of the Brownian motion in the next clip. So there's a good exercise in using the properties of Markov chains and conditional probabilities, conditional expectations. So I have here a couple of alternative ways you can prove it. One is, I guess this would be called a law of total probability, where you start out with the probability of of s at time k being in state n, and you say, well, what can I do with it? Let's apply a sort of first step transition analysis idea, where you condition on where the chain might have been on the time right before. So time k is on the left hand side, we're going to condition on where the chain was in the previous step. So let's suppose that the chain the random walk was in state z on the previous time step. Now we have, we're basically going to say the probability that it was in z on the previous time step times the probability that it went from z to n is exactly the probability that it is in n at time k, unconditionally. So here I'm summing up over all possible states where the chain was on the previous time step. And we've seen these calculations before. And how does the sum break down? Well, to get to state n, the only way to get there is from state n minus 1 or n plus 1. And so that's why I'm summing these two things here. So the sum really has only two terms in it, corresponding to the states from which I could have gotten to state n. So this one says I could get to state n from state n minus 1. And this one says that the random walk could get to state n from state n plus 1. And these are my probabilities that correspond to the fact that I was in those states at one time step before. So the leading terms here, you just recognize them as one-step transition probabilities of Markov chain. And in this particular example, we saw that they don't even depend on the current state. So here the state is n plus 1, but the probability of going to n is still 1/2. Doesn't depend on n. Still Markov transition probabilities though. And same thing here. If you're in n minus 1 and you want to transition to n, the probability of that is again 1/2. So you pick up these coefficients of 1/2 in front of the two unconditional probabilities, and we're kind of almost there. We see that we have a similar, very similar structure. We definitely picked up the same 1/2 coefficients on each of the terms, and now the only thing we need to do is identify this probability with f at t minus delta x minus delta, and that probability there, I guess it's maybe the other way around. You can kind of tell already that n plus 1 is going to be associated with this term, and the n minus 1 is going to be associated with that one because I'm subtracting a delta x here. So before, I'm going to do that over here, but before that, just so you're kind of aware, there's a different way of computing this out. In fact, the way you get to this statement often is by taking the route of conditional expectations. So this is sort of an alternative proof of the very same thing, just to kind of lead you through it. You start out with this probability and write it as an expectation. So expectation of an indicator is the probability of that event. Here I'm conditioning on the previous step. This is kind of like a first step transition analysis. So I'm looking at a 0, 1 variable of whether the random walk at time k is in state n, and I'm going to condition on where it was in the previous state. And now I've just made my problem slightly easier because I know how to compute this inner expectation. And now I've taken that inner expectation and just called it g. What is that inner expectation? Well, it's just the probability. So this inside term here represents the conditional probability of starting from some sk minus 1, wherever this was, and transitioning to state n. And so I've defined my function g right here. So we've seen this calculation in a number of different settings so far. So this is the conditional probability of being in n at time k, given on the previous step we were in state z, and z here represents this variable, the location of the chain at the previous time step. And clearly this is 1/2 whenever z is 1 away from the current state. So the only way to get to n is just like the logic we used here. The only way to get to n is either from state n minus 1 or n plus 1. And so when z is in one of those, n minus 1 or n plus 1, you'll get that the probability of going there is 1/2. And then, once you have this, you just plug it in. How do you evaluate this expectation? Well, it's, this takes on the value 1/2 with probability, with this probability, and this takes on the value 1/2 with that probability, and so you're done. Now, so the only final part is relating these two unconditional probabilities to these terms in terms of the continuous variables t and x, and this is pretty easy. You just note that you have these conversions for you. The time step k is just t divided by delta t, And so what's k minus 1? I just plug it in. This is my k. This is my 1. You can see that the integer part of this, right, if you have, say, a value 3.75, you take the integer part and subtract 1, you get 2. Well, if you take 3.75 and subtract 1, you get 2.75, and the integer part of that is 2 again. So it shouldn't be too difficult to convince yourself that this 1 just slides into the integer part. And now I write it like this, which tells me that k minus 1, which is in both of these probabilities, is associated with the value t minus delta t. On this side, t was associated with the k, which is t over delta t, and on this side I have t minus delta t, which is now associated with k minus 1. So that's step 1. Step 2 is, I do the identical thing. Now I have a plus and minus 1. So this set of steps works exactly as up here, and it works with both the n plus 1 and the n minus 1. So you pick your favorite, let's say plus x over, this is my n plus 1. The plus 1 comes in. The integer part of 3.1 plus 1 is the same thing as the integer part of 4.1 plus 1. And now just write it in this form, and now we see that n plus 1 corresponds to x plus delta x, and n minus 1 corresponds to n minus delta x. And so here you have n plus 1, it corresponds to this term, and here you have n minus 1, which corresponds to that term. And so, using the definition, you plug it back in and you get this lemma. And while it may seem unclear as to why I'm doing this, we'll see the reason for it in the next clip.